Hello, friends. You're welcome to today's lesson. Today, we are going to be solving some of the questions we are given as a take home in our previous lesson on velocity time graph. If you've not seen that very lesson, please, I would love you to go ahead and see that very lesson. So, in that previous lesson, we did a whole lot of work on velocity time graph. We said that velocity time graph is an acceleration graph. A whole lot was said on it, and we are given some questions, some quite and witty questions to test ourselves to see how much we got from that lesson. So sit back, get some popcorn, and take a ride at me, even as I solve all those questions one after the other. So this was the very first question we were given as a take home. A car starts from rest and accelerates uniformly for 5 seconds until it attains a velocity of 30 meters per second. It then travels with a uniform or constant velocity for 15 seconds before decelerating to rest in 10 seconds. Now, this question was given to some NECO students in 2009. So we're asked to solve for a couple of things. So the very first thing we asked to solve for, we asked to sketch the velocity time graph. Very important. The next, we are asked to solve for the acceleration during the first 5 seconds. And also, we are asked to get this deceleration during the last 10 seconds. And lastly, we are asked to solve for the total distance covered during the motion. So first of all, we're going to be drawing the graph. We're going to be drawing the velocity time graph. Now look at the question. A car starts from rest and accelerates uniformly for 5 seconds until it attains a velocity of 30 meters per second. So this velocity is a max velocity or the max speed. So let's quickly solve. Let's plot our graph. Let's draw a velocity time graph, So right here, this is what we have. This is what we have right here. So right here, this is velocity, which is a meter per second, while this is time, which is in seconds. So the body started from rest. Now for the fact that the body started from rest, don't forget, so the body started from the reference point, like this. So the body started from rest and moved up to 30 meters per second, accelerated up to 30 meters per second. That was the max speed the body attained. The body attained a max speed of 30 meters per second. So here, 30 meters per second. And this whole journey happened between that for the first 5 seconds. It took the body first 5 seconds to get to this max speed of 30 meters per second. Don't forget, from zero reference point, now the body moved from 0 to 30 meters per second. Now it took the body just 5 seconds. So let's say from this rest point to point A. So this is how to draw it. Now don't forget, a car starts from rest and accelerates uniformly for 5 seconds until it attains a velocity of 30 meters per second. We've drawn that already. Then it then travels with a uniform or constant velocity for 15 seconds. So it continued at this very speed or at this very velocity for another 15 seconds. That's very easy to interpret. So this continued for another 15 seconds. And let's see the next line of statement. The next statement. So it then travels with a uniform velocity for 15 seconds before decelerating to rest in 10 seconds. So after traveling, at this speed of 30 meters per second for 15 seconds, let's see, that's going to be a new time. So 15 seconds added to the first 5, that will be 20. Don't forget, the time is in seconds here. Then it decelerated. It came to rest. It came to rest in 10 seconds. The body came to rest in 10 seconds. The body decelerated in 10 seconds. The body decelerated in 10 seconds, just like this. The body came to rest in 10 seconds. So from point A, or from 0, reference point to A, from A to B, now from B to C. So it took it another 10 seconds to come to rest. So add the 10 to the 20, we have a final 30. So this is how to draw the velocity time graph, as simple as that. The body started from rest, accelerated uniformly for some time until it got to 30 meters per second, max speed. Now it took that body 5 seconds just to achieve this. From nothing, to 30 meters per second, it took it 5 seconds. So from 0 to point A, now it maintained that same speed for another 15 seconds. So that's from point A to point B. Now before coming to rest in the next 10 seconds, it came back to rest. So we've drawn the graph already. So the next thing we're going to do now is to start calculating. Let's start solving for other things. We're going to be solving right now. So the very first question is solve for the acceleration during the first 5 seconds. So the body accelerated during the first 5 seconds. Uniformly, it did. So let's solve for acceleration during the first 5 seconds. Now don't forget, acceleration, which is same thing as average acceleration, is same thing as change in velocity over time taken, or change velocity over change in time taken also. So acceleration is a vector quantity. So the body started from nothing and accelerated up to 30 meters per second. So that'll be 30 meters per second minus 0 meter per second over a change in time. We took it 5 seconds, said earlier. So 30 minus 0, that'll be 30 meters per second over 5 seconds. So you're going to divide 5 here, 1, 5 here is 6. So that's a 6 meter per second squared. That is the acceleration of the body. That's the acceleration of the body during the first 5 seconds. So let's quickly solve the third question. We're asked to solve for the deceleration during the last 10 seconds. So the body decelerated back to rest uniformly during the last 10 seconds. So deceleration, don't forget, deceleration is the same thing as acceleration, but this time around it's a negative acceleration. So we're going to call this negative acceleration, which is deceleration. We can call this D, that's deceleration. Instead the same thing as change in velocity over time taken. That is deceleration. So the new final velocity is 0 meter per second minus initial speed, 30 meter per second, over the time, which is 10 seconds. So what do we have? 0 minus this, don't forget, minus this. So 0 minus this minus 30 meter per second over 10 seconds. So minus takes up minus. So what do we have? 10 here 1, 10 here 3. So it's 3 meter per second squared. That is our, deceleration in the last 10 seconds. So quickly, we're going to be looking at the last question, which is the total distance covered by the body. Don't forget that for the total distance covered by the body is simply the area of this very shape that we have here. Okay, the total distance traveled or covered by the car. Let's quickly see how to get that. So don't forget, total distance covered by the car is going to be the total area of this very shape that we have here. So that's going to be total distance covered is area of shapes. That's the total area of the shapes. So we have the first shape, shape A, shape B, and shape C. So you're going to get the area of each of the shapes. Now we are very much aware of why we have to get the area of this very shapes. Why area of the shape is equals to the distance covered by that very, car. So don't forget, we have this time in seconds, this velocity in meter per second. So how do we get displacement or distance covered? Velocity or speed is equals to distance over time taken. So if speed is distance over time taken, then distance is going to be speed times time. So if this is speed and this is time, so speed times time is more or less like saying area of this triangle. So let's get the area of the first shape. So area of shape A, that's what we're about to get. Area of shape A that's area 1. It's half of the base times height. Half of the base times height. So that's going to be 1/2. The base is 5 seconds. Then the height is 30 meters per second. So 2 year 1, 2 year 15. 15 times 5 give us 75 meters. So shape A gave us on the 5 meter distance. So the next thing we're going to get is area of shape B. Area of shape B. Let's get area of shape B now. Don't forget, shape B is a rectangle. Shape A is triangle. Shape B is a rectangle. So area of shape B, area 2, is just length times breadth. That's just it. Length times breadth. That's it. So what's the length? The length is what we have here, which is 30 meters per second. 30 meters per second. While the breadth is the 15 seconds. That's what we have. We're almost there. We're almost there. So 30 times 15 will give us 450 meter. We're done with that. So area of shape B is 450 meters. So at that very point, from point A to point B, the body covered 450 meters. So we're going to solve for the very last one, the last shape. The last shape is another triangle. That was when the body decelerated. So let's get that area of shape B, area of shape C, area of shape C. So area of shape C also is a triangle. So 1/2 times base times height. That is a triangle up there. So 1/2 times the base is 10 seconds, the height is 30 seconds. So that'll be 1/2 times 10 seconds base times the height 30 meter per second. So 2 year 1, 2 year 5. 5 times 30. 5 times 30 will give us 150 meter. So now we have everything set out. So what is the total distance covered by the body? The total distance covered by the body, total distance is simply this. Let's see what the total distance is. You're going to add up everything. That's 75 meter plus 450 meter plus 150 meters. So 75 plus 450 plus 150. So let's do the math. So 75 plus 450, that will give us 525. So 525 plus this will give us 675 meters. So total distance covered by the body is 675 meter, which is saying as if we convert it to kilometer, is 0.675 kilometer. So as simple as that. Question 2. A body travels in a straight line and the speed at any time does not exceed 5 meters per second. If it accelerates and decelerates uniformly at 2 meters per second squared, find the shortest time required to cover a distance of 30 meters from rest to rest. Now, as you can see, a body travels in a straight line. Now, for the fact that the body travels in a straight line, it could be that the body accelerated, or the body accelerates, I beg your pardon, from rest, or the body decelerates, or the body maintained a constant speed attained. Now, if a body travels in a straight line, it could be either of those three things I've mentioned. But we're going to try to interpret what this simply means. A body travels in a straight line and the speed at any time does not exceed. Now, if the speed does not exceed 5 meters per second, it simply means 5 meters per second, is the max speed or the max velocity attained by the body. So now look at the main question. If it accelerates and decelerate uniformly at 2 meters per second squared. Now, this is simple to interpret. Now, there's it. The body started from here. Let's draw our velocity time graph first to help us interpret this. There's it. Don't forget, velocity is a meter per second right here. And our time is in seconds. So we're told that if it accelerates and decelerates at 2 meters per second uniformly. So the body did two things in quick succession. The body accelerated or accelerates, as we said there in present tense. Then the body decelerates also. So it accelerates and decelerates. Now the two phenomena or the two scenarios, it was 2 meters per second squared on both occasions. So the body accelerates from rest, from zero. Accelerates. Now it took it some time to do that. Let's assume we don't know what the time is. We're not told, and that's what we're asked to get. So the body took it some time to accelerate, and when it accelerates, it's only got a max speed of 5 meters per second. The speed attained did not exceed 5 meters per second. So that's just that here. Speed of 5 meters per second. Now, how long did they take it? We don't know. We're not told. Just assuming that it took it X seconds. So it's also decelerated another 2 meters per second squared. The first acceleration, 2 meters per second squared. The second deceleration, which is negative acceleration, 2 meters per second squared also. Now from point 0 to point A, and from point A to point C. Now take the body, let's say another y seconds. We are not told. So yes, s plus y right here. S plus y right here. So the body accelerated, or accelerate, 2 meter per second, and then decelerate 2 meter per second. Everything was uniform, as been stated up there. Now it took the body, the body covered 30 meter. That's the total distance from rest to rest, 30 meter. So we're not told the time, but we're asked to get the shortest time that is required to cover a distance of 30 meter from rest here to another rest here. So it's very simple. We have two shapes right here, shape A and shape B, and they are both triangles. So it's going to be area 1, area of shape 1, area of first shape, which is shape A, half times base times height. So that's 1/2. The base is x seconds. We assume that it's x seconds. We are not told. The height is 5 meter per second, because that's the highest height. So what do we have? Is 5x over 2 meter. That's what we have. So next, area 2 is also half times base times height. So that's going to be 1/2 times base. The base is y seconds. The height is also 5 meter per second. So what do we have altogether? We have 5y over 2 meter. So we're going to combine these two together. When we combine them, we're going to have 30 meter as stated. So area 1 is 5x over 2 meter. Don't forget, we saw that already up there. Area 1 is 5x over 2 meter. Then area 2, that's area for the second shape, is also 5y over 2 meter. Now it was said that it took the body, just 30 meter. We asked to get how long it's going to take the body. That's the time taken for the body to cover a 30 meter distance from rest to rest. So total distance is 30 meter from rest to rest. So let's solve that. Let's do that. So total distance, which is 5x over 2 meter plus 5y over 2 meter equal to 30 meter also. So we're going to combine them at the top. So that's 5x plus 5y over 2 equals to 30 over 1. We can cross multiply. That's 5x plus 5y equals to 2 times 30 is 60. So 5 is common. Bring the 5 out, x plus y equal to 60. Divide both sides by 5. So x plus y equals to 12. That's 12 seconds. So it took the body 12 seconds to cover a distance of 30 meter from rest to rest. That's simple. Don't forget that Don't forget that for the body to accelerate first from rest, it's accelerated 2 seconds down to 15 meter. Down to the max speed that we had there. It took it x seconds. So it also took it another x seconds to decelerate down to rest. So the total time taken for the body to cover 30 meter distance from rest to rest is simply 12 seconds, as easy as ABC. Question 3, the third and the final question. Now look at this question. This question is witty and it will demand you to really think. It was very simple. A train accelerates uniformly from rest at a station A to a maximum speed of 80 km per hour. Don't forget, velocity is a meter per second. Now, but due to probably how complex this question is, we could decide to leave the speed, our speed at kilometer per hour. Then later on, we could do a form of conversion, and then maintain the speed for a certain time. It then decelerates uniformly to come to a stop at station B, 60 km from A. The time taken from A to B is 1 hour. If the rate of acceleration is half the rate of deceleration, find A, the acceleration in meter per second squared, then B, the time during which the constant speed was maintained. Now the question is very simple. Before we could solve for any of this, first of all, the first thing we have to get is our velocity time graph. We have to look for a way to draw our velocity time graph. So that's what we're going to do right now. We're going to be drawing the velocity time graph. A train accelerates uniformly from rest at the station A to a maximum speed of 80 km per hour. So let's see what that looks like. Let's see, the velocity time graph is very important. So here, so velocity, that's always in meter per second. We're going to let it be in kilometer per hour this time around. You can also convert it, but if you convert, you may end up with some complex stuff to to deal with. So the time is an hour this time around. Normally it should be in seconds. So a train accelerates uniformly from rest at a station A. So the body started from rest, accelerate uniformly from rest at the station A. So there is a station, let me say, yeah, station A, that's from rest, this station A. The body accelerates uniformly from rest at a station A to maximum speed. The body got to maximum speed of 80 kilometer per hour. So the body got to maximum speed of 80 kilometer per hour. That's a maximum speed of 80 kilometer per hour. There's a max speed. Now, we are not told how long it took the body to get to this 80 kilometer per hour. So we're going to assume that it took it some couple of hours. So we're going to assume that it took it, let's say, X hours. It took it X hours. So it's going to be X from A to B. Then, what's the next line of statement? And then maintain this speed for a certain time. Now, this speed was maintained. The speed was maintained for a certain time. The speed was maintained for a certain time. Now, we are not told also the time, how long it maintained the speed. We are told that the speed was maintained. Let's say it took it another Y hours for the speed to be maintained. That's going to be X plus Y. It then said maintain the speed for a certain time. It then decelerates uniformly to come to a stop at another station. So let's say look at this A. Let's call this P, from A to P, then P to Q, A to P, P to Q. Then it's then deceleration uniformly to come to a stop at station B. Now it came to rest. Decelerates uniformly from this place. Came down to rest at station B. These are train stations. So from A to P, the body accelerates. We are not told the acceleration. Then the body maintains this acceleration. Accelerate from A to B, from A to P, took it X hours. Then from P to Q, maintain the same 80 kilometer per hour speed attained. It took it Y hours. Then from Q to station B, it took it some more time. We're not told the time it took it. We assume that it's Z hours. So here, right here, we have S plus Y plus Z at this very spot. That's what we have. So we've interpreted this already. So let's look at other statements, the other things we are given. It then accelerates uniformly to come to a stop at station B, 60 kilometer from A. So station B is 60 kilometer from station A. That means the whole distance covered by the body is 60 kilometer, as simple as that. Station B is 60 kilometer from station A. So they said the time taken from A to B is 1 hour. Now I take this body, this very train, 1 hour to travel from A to B. So that means the total time taken is 1 hour. That's just what it simply means. So let's quickly write it out. So X hours plus Y hours plus Z hours is equals to 1 hour. That's what we have. So we have this already sorted. So it took it 1 hour the whole time. So then we also told, they said, if the rate of acceleration is at the rate of deceleration. So let's also interpret that very line of statement. Now, acceleration, which is change in velocity over time taken. So acceleration, change in velocity from 0 to 80 kilometer per hour, So that's 80 kilometer per hour minus 0 kilometer per hour over X hours time. So that will give us 80 kilometer per hour over X hour. So acceleration is 80 over X in bracket kilometer per hour squared. So we know what acceleration is. It's well solved for. So they said acceleration is half the rate of deceleration. So you're going to get deceleration right away. Deceleration, which is negative acceleration. You know what that is? Change in velocity also over time taken. So let's get deceleration. So what's the change in velocity? The body was at 80 kilometer per hour. came down to rest 0 kilometer per hour. So that's going to be change in velocity, which is, you know what that is? Change in velocity, acceleration here. Deceleration is negative acceleration. So that'll be 0 kilometer per hour minus 80 kilometer per hour over the time z hours. That's why we have that from here to here. So we're almost there. So that's going to be minus deceleration, which is negative acceleration, minus 80 kilometer per hour over z hours. So this can take out this. So deceleration is 80 over z kilometer per hour squared. That's what deceleration is. So we're told that acceleration is half the rate of deceleration. So this is a very simple and direct stuff. So acceleration is 1 over 2 times deceleration. So what does that mean? If acceleration, we got our acceleration as 80 over s kilometer per hour squared. So what it means is 80 over s kilometer per hour squared is equals to half. Acceleration is half. That's when you need to get acceleration, you need to divide deceleration into two parts. 1 over 2 times 80 over z kilometer per hour squared. This could take out this. So 2 year 1, 2 year 40. Or retardation. So we got this 80 over s equal to 40 over z. So it's high time for us to carry on to solve for all the questions we are given. Don't forget that total time taken up there, as stated, it took the body 1 hour to complete 60 kilometer distance between station A and station B. They took the train 1 hour to complete it. So everything is already set. So first of all, let's get our total distance. You're going to be getting a couple of equations. So you need your arithmetic ability to be, up to average for you to understand what you're about to solve. So let's get the total distance. We have 3 major shapes here. We have shape A, shape B, and shape C. So shape A is a triangle, shape B is a rectangle, shape C is another triangle. So first of all, area of the first shape, area 1, is half of the base times height. That's what we have for area 1. So let's quickly solve that. Area 1 was half of the base. What's the base? The base is x hours. It's x hours. And then the height, what's the height? The height is 80 kilometer, I beg your pardon. 80 kilometer per hour. So 2 year 1, 2 year 40. So what do we have for area 1? Area 1 is 40x kilometer. That's what we have. That's that for area 1. So quickly, let's get area 2. Area 2 is the length times the breadth. That's area 2. So what's the length? The length is 80 up there, 80 kilometer per hour, while the breadth is the y hours. So altogether we have 80y kilometer. 80y kilometer. That's fine. So the next you're gonna get area 3. Area 3 is 1 over 2 times the base times the height. That's what we have for area 3 also. So what do we have? We have 1 over 2 of the base. So 1 over 2, the base for area 3 is z hours. Then the height remains 80 kilometer per hour. That's the max height. Nothing changes that. So what do we have? We have 40z kilometer. So we have all the distances. For the very first, we have 40 times s. This 40x, I beg your pardon. This 40x kilometer. Second, 80y kilometer. And the very last, 40z kilometer. By the time we add all this, by the time we add 40 kilometer, 40s kilometer, 80y kilometer, and 40z kilometer, you're going to get in the 60 kilometer that the train covered between station A and station B. As simple as that. So let's sum them all up. That's 40x kilometer plus 80y kilometer plus 40z kilometer equals to 60 kilometers. Right here, we can forget about all the kilometers. They can take out all each other. So you can take out the zeros. 2 year 2, 2 year 4, 2 year 2, 2 year 3. So what do I have left? And all this km could take out, so we have 2x plus 4y plus 2z equals to 3. So we could call this a given equation 1. I could call equation 2 right there because right here we have equation 1 already up here. This is the first equation. So we're almost where we want to be. So don't forget what we are told. We have 80 over x equal to 40 over z there also. So we're going to use that. So let's bring that down. Say 80. You have 80 over x equals to 40 over z. So let's do something. Let's cross multiply. So 40 comes here, x comes here. So we're going to end up with x over z equal to 80 over 40. So x over z equals to 2. So x is equal to 2z. This is another important piece. You can call this equation 3. So we're going to be solving this simultaneously. We're going to be using our substitution method. So if x is equals to 2z, I could fix it in here. X is equal to 2z. Don't forget that up there we have x plus y plus z as 1. X plus y plus z as 1. That's another very important part. I call that equation 1. So x is equal to 2z. So if x is equal to 2z, it's very simple. We're going to use our substitution method to get all this, to get this solved right away. So x is 2z, so we can fix it here. S 2z plus y plus z equals to 1. So what I'm going to do next, so 2z plus z plus y equals to 1. So this right here, we have right here, this is 3z plus y equals to 1. So y is same thing as 1 minus 3z. So we have another stuff here. We've got our y. So our y is 1 minus 3z. Our x is 2z. Now how do we get y as 1 minus 3z? I fix this into this. So I can come here and fix every one of them into this place to get the value of z. So let's see what we have right there. So 2x, x is z, s is 2z, I beg your pardon. So that's 2 open bracket 2z plus 4y. Y is 1 minus 3z, then plus 2z equals to 3. It's sorted already. 2 times this is 4z, plus 4 times 1, 4, minus 12z, then plus 2z equals to 3. So you're going to call that like terms. So 4z minus 12z plus 2z, as simple as that. Send this on to the other side. So 4z minus 12z plus 2z equals to 3 minus 4. So we're almost where we want to be. So 4z minus 12z is minus 8z. Minus 8z plus 2z will give us that's minus 10z. 4z minus 12z is 4z minus 12z is minus 8z. Minus 8z plus 2z. Minus 8z plus 2z will give us minus 6z. I beg your pardon. Minus 6z. So 3 minus 4 is minus 1. So divide by 7 minus 6. Minus 6. So z is 1 over 6. So we've already gotten a portion of the time taken. We've gotten our z as 1 over 6. So if z is 1 over 6, it's very simple for us to get what our y would be. It's very simple. So you're just going to fix it in this simultaneous equation. There's no big deal here. So our y is going to be 1 minus 3 times 1 over 6. That's what we have here. So 3 here 1, 3 here 2. So our y is 1 minus 1 over 2. So 1 minus half is half. So our y is 1 over 2, as easy as ABC. So quickly, let's look for a way to get other things. Let's get other stuff. You're going to get other stuff right now. So let's get other stuff. We have our y to be 1 over 2. We have our z to be 1 over x. So if our y is 1 over 2, our x is 1 over 6. So what's going to be our x then? What's going to be our x? Don't forget x is 2z. X here is 2z. So if z is 1 over 6 and x is 2z, you know what x is going to be then? So x is going to be 2 times 1 over 6. So x is 1 over 3, as simple as ABC. So x is 1 over 3, y is 1 over 2, z is 1 over 6. So let's come back. Let's go back to the very time graph. Let's go back to the very time graph. Our time graph up there. So let's try to interpret. Let's try to make sense of this. So our x is 1 over 3. So it means it took this body 1 over 3 seconds at the very beginning. It took it 1 over 3 seconds at the very beginning. That's what it took it. 1/3 hour. I mean 1/3 hour at the beginning. So after I took it 1/3 hours at the very beginning, then I took it another 1/2 hours, that's half hour, to maintain that very speed. That's for y. It took it another half hour, 1/2 hour, that's 30 minutes. And finally, it took the body 1/6 hour to come down to rest. 1/6 hour to come down to rest. That's about 10 minutes. 60 minutes make 1 hour. So that's 1/6 hours. So as simple as that. See how very easy it is. So now we are asked to get the acceleration. We are asked to get acceleration, and also we are asked to get the time it took it to maintain that very speed. That's already solved. 1/2 hours, which is 30 minutes. So quickly, let's solve for the acceleration. Let's solve for the acceleration. That's what we're about to do right now. So acceleration of the body. Acceleration of the body, that's what we have to get. We have to get the acceleration of the body, acceleration in meter per second squared, and the time during which the constant speed was maintained. So acceleration in meter per second squared. So what's acceleration? Acceleration, the change in velocity over time taken. So the change in velocity of that is 80 kilometer per hour. Now, what's the time? The first time, which is x, the first x is 2z, z is 1/6, so x is 1/3, so that's 1/3 hour. So what do we have? We're going to solve this simple. So I think you equate the 3 comes out, 1 stays out. That's 240 kilometer per hour squared. This is what we have, 240 kilometer per hour squared. So you're going to look for a way to convert. 240 kilometer per hour squared to meter per second squared. So that's just that. Now don't forget the time it takes the body. The time it takes the body is 1/2 hours, which is 30 minutes. That's already sorted. So we're going to convert this right now. So 240 kilometer per hour squared to be converted to meter per second squared. So it's very simple. Don't forget this was the acceleration the train moved with. That's from rest, moved with 240 kilometer per hour squared acceleration. But we're asked to convert this to meter per second squared. So let's quickly see the relationship between kilometer and meter, then hours and seconds. Now don't forget kilo is a multiple unit. So it means 1,000 meter make 1 kilometer. Why 60 seconds make 1 minute? 60 minutes make 1 hour. So if 60 seconds makes 1 minute and 60 minutes make 1 hour, it means 3,600 seconds make 1 hour. So why here 1,000 meter is in 1 kilometer. So we're going to convert this 240 kilometer over 1 hour times 1 hour. I'm trying to make it easier for you to understand. So 240 kilometer 1 hour times 1 hour. 1 times 1 is 1. Hour times hour is hour squared. So we're going to be converting 1 hour to second, another 1 hour to seconds. So 240 kilometer to meter. Don't forget, in 1 kilometer, there's 1,000 meters. So in 240 kilometer, imagine you're going to be having 240 times 1,000. So 240 times 1,000 over. Now in 1 hour, we have 3,600 seconds. That's what we have in 1 hour. So in another 1 hour, 3,600 seconds. So this is how to convert. So you're going to divide, let's break them down. 2 zeros here, take out those 2 zeros. 0 takes out 0. 0 takes out 0. So what do we have next? 4 can go in there. 4 can go here. And 12 can go here. Let me just use 12. 12 here 2. 12 here 3. 2 here 1. 2 here 18. So what do we have? 1/54 meter per second squared. As easy as ABC. So don't forget, while the time it took it is 1/2. That is the time, 1/2 hour or 30 minutes. Took the body 1/2 hour to maintain speed. So this is everything for the take-homes we were given in our previous lesson. So if you got them right, it means you understood the velocity time graph 100%. And so we've come to the end of velocity time graph. So in our next lesson, we're going to be looking at instantaneous acceleration and velocity and so on. So at this very point in time, we'd read the content of today's exposition. If you found this lesson resourceful, please subscribe to this very channel and share this lesson with others. See you in the next lesson. Thanks.